So section 8.5 is all about the graphs of quadratic functions. Friendly reminder that the domain of a relation, also known as a function, right, is the set of all possible values of x, and our range of a function or relation is the set of all possible values of the dependent variable y. And this is important because all quadratic functions, whose graph is a parabola, those are functions. All quadratic equations give us a function. So a function f is a quadratic function if it takes the form ax squared plus bx plus c, where a, b, and c are real numbers with a not equal to 0. It's really important that a doesn't equal 0, because if a equals 0, we would have a linear equation. The graph of any quadratic function is a parabola, right? They could look like this, or I could have one that's upside down, and they have a vertical axis of symmetry through a very special point. This is the point where our slope changes from decreasing to increasing, or increasing to decreasing, and that point is going to be called the vertex, and it's what we're going to talk a lot about for the remainder of this chapter. So here's our most basic quadratic function. It's the squaring function, x squared. So what this function does is it takes every x value and pairs it with its matching perfect square for its y value. So -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 is 4. Notice it has a line of symmetry right through the middle when x equals 0. The domain of this function is from -infinity to +infinity. This is an important thing to memorize. This is the domain for all quadratic functions. What changes when it comes to a quadratic function is the range. The vertex of this function right here is our origin, right? Our vertex is where our slope changes from decreasing to increasing, or vice versa. It has an axis of symmetry, and it is continuous over its domain. What does it mean to be continuous over its domain? To be continuous over its domain in this class means I can draw it without picking up my pencil. That's how we're going to define continuous over our domain. The thing is, when we see quadratic functions, they don't always look like this, right? We get things that look like f of x is 2x squared minus 3x plus 4, right? So how am I going to graph this? Well, and what does this graph look like? That's what we're going to spend section 8.5 and 8.6 trying to build up to understand. So the first thing we need to understand is how I could shift my graph around our xy coordinate plane. The first type of shift I have is a vertical shift of a parabola. So if I have f of x equals x squared plus c, right, this is going to have the same shape of my perfect square graph, but it's going to be shifted k units along the y-axis. Okay, so its vertex is going to be 0k, and its axis of symmetry stays the same. So let's take, for example, f of x equals x squared minus 2. And I'm going to show how this is going to shift our graph. So if I have -2 squared, that's going to be 4 minus 2 is 2. -1 squared is 1 minus 2 is -1. 0 squared minus 0 is -2. And we have symmetry. So my graph is going to be shifted down to -2. When x is before, when x was 0, so this is our origin. Now we're going to be shifted down to. When x is -1, y is -1. So that's 1, -1. And when x is 2, y is 2. Okay, so here's the graph of my new parabola. It is our original parabola just shifted down 2. We can also have a horizontal shift of a parabola. If I have f of x is x minus h squared, and it has the same shape as the graph of f of x equals x squared, this graph is shifted h units along the x-axis, so horizontally, and its vertex is h, 0. Okay, so let's take a look at f of x equals x minus 2 squared. What this graph is going to do, even though we're subtracting, it's going to shift it to the right too. Let's take a look at how this affects our points on our parabola. Negative 2 minus 2 squared is negative 4. Oh my gosh. Negative 4 squared is 16. That's really big. Negative 1 minus 2 squared is negative 3, which gives us a 9. 0 minus 2 is 4. 1 minus 2 is 1. 2 minus 2 is 0 squared is 0, right? So it shifts our graph to the right too. If I have f of x, I don't know why I put that extra parenthesis there, but f of x equals x plus 3 squared, this is actually going to shift to the left 2, left 3. Okay, so it's important to remember that for horizontal shifts, we're looking at the opposite. So here are some graphs, some equations that I want us to see. So f of x equals x squared plus 3. This is a graph shifted vertically 3. If I wanted to shift my graph horizontally, like so negative 3, this would be shifted to the left. I'd actually add. If I want to shift my graph vertically, I'm going to subtract negative 2. So this is shifted down, whereas this one's shifted up. Shifted horizontally a positive 2, this is shifted to the right. So it's important for us to be able to look at these equations and see how our graph has been moved. So here's how it comes all together. So H is our horizontal translation, right? K is our vertical translation, and A represents a reflection across the x-axis or a vertical stretch or compression. Remember, if A is negative, my parabola opens down. That means it's flipped, right? Instead of being facing up, it opens down like so. So here's some characteristics of our parabolas. So I've got f of x equals a times x minus h squared plus k, okay? This is a parabola with vertex hk. Its axis of symmetry is x equals h. If a is positive, my graph opens up. If a is negative, my graph opens down. My graph is wider if a is a fraction, right? A number between 0 and 1. And it's narrower if a is greater than 1, okay? So why don't we go ahead and graph f of x equals negative 2 times x plus 3 squared minus 4. And we'll take a look at what this graph looks like. So I have the function f of x equals negative 2 x plus 3 squared minus 4. So we're going to take our original parabola, and I know a couple things from looking at my equations. So 1, this is shifted down 4. This is shifted left 3, right? That's going to take my original parabola whose vertex was 0, 0, and it's going to go down 4. Should probably go ahead and label this beautiful coordinate plane and draw this in a different color. So I go down 4 over 3. So here's my new vertex. And I know something else. I know that my parabola opens down. So if I'm going to graph a parabola, I need 3 points. So I'm going to pick some x values that are really close to the one point I already have. So when x is negative 3, and y is negative 4. Okay? So I'll have negative 3. I know at negative 3y is negative 4, or f of x. Remember, f of x equals y. I'm also going to take a look at negative 4 and negative 2. I want to pick the 2 points closest to negative 3. So I have negative 2 times negative 4 plus 3 squared minus 4. That gives me negative 4 plus 3 is negative 1. Squared is a positive 1 times negative 2. So I get negative 2 minus 4, which is negative 6. Now, we have symmetry. So if I have 1 point away from negative 3, and then I'm another 1/4 away from negative 3. This is also going to be negative 6. So let me show you. Negative 2 times negative 2 plus 3 squared minus 4. Negative 2 plus 3 is 1. 1 times negative 2 is negative 2. Negative 2 minus 4 is negative 6. We have a line of symmetry right through here. This is the line x equals negative 3, and this is my line of symmetry. So I can go ahead and graph my parabola. I'm going to answer a couple more questions because I like to know lots of things about my parabola. So my vertex is when x is negative 3, y is negative 4. My line of symmetry is x equals negative 3. My domain is always from negative infinity to positive infinity, but what changes is my range. In this case, my range goes from negative infinity, right, that's what's all the way down here, negative infinity, all the way up to negative 4, and negative 4 is included. So my range goes from negative infinity to negative 4.